Hi, my name is Christian Clanton. I'm a third-year graduate student at The Ohio State University. In this short video, I will discuss the results of a couple recent papers I have submitted to the Astrophysical Journal with my PhD advisor, Scott Gaudi, on the frequency of planets around M-dwarfs. Perhaps surprisingly, we know more about the planets orbiting M-dwarfs than all other types of stars. The constraints we have on the giant planet frequency around M-dwarfs are derived from several techniques, including radial velocities, or RV for short, and microlensing. Here, we see two figures plotting log planet frequency around M-dwarfs as a function of log planet mass on the left and as a function of log orbital period on the right. For reference, I have shaded the region corresponding to giant planets in the left plot, and I have marked the approximate location of the ice line for a 0.5 solar mass star on the right plot. The sample of RV monitored stars from the California Planet Survey has indicated that the frequency of giant planets around M-dwarfs is quite low. The RV survey of HARPS includes a sample of M-dwarfs which also yield a low occurrence rate of giant planets. However, microlensing surveys have found occurrence rates of giant planets, albeit planets that are somewhat less massive than those found by RV, but nevertheless still giant planets, that are more than an order of magnitude larger than those inferred from RV studies. On the other hand, microlensing is sensitive to larger orbital separations than RV, typically detecting planets beyond the ice line. Understanding the difference in the planet frequencies as inferred by RV and microlensing is an important question because these two methods are probing different populations. In the core accretion paradigm, giant planets are believed to have formed beyond the ice line, so the majority of giant planets detected by RV must have migrated, whereas those detected by microlensing have presumably formed in situ or have at least not migrated very far. There are several potential explanations for the large difference in inferred giant planet frequency around M-dwarfs, but perhaps the simplest are the different ranges of orbital period and planet mass probed by these two methods. In principle, the properties of the observed sample of host stars by microlensing could well be different from those of the local RV samples, leading to more complicated explanations. In this study, we aim to determine whether or not the microlensing and RV results are consistent, and to determine what, if any, joint constraints on the planet frequency around M-dwarfs can be derived from these two techniques. The typical planet discovered by microlensing is found around a 0.5 solar mass star and has a mass of about that of Saturn and a projected separation of about 2.5 AU. Assuming such a planet is on a circular orbit and has the median values of a randomly distributed orbit for the rest of its orbital parameters, it will have a period of about 7 years and produce an RV semi-amplitude of about 5 meters per second. Such a planet is just detectable with state-of-the-art RV surveys. However, allowing the system's orbital parameters to vary results in a distribution of RV observables, only a fraction of which are now detectable. Including the full range of planet and host star properties from microlensing surveys further broadens this distribution of properties of RV analogs. We find the median RV semi-amplitude for all microlensing planets to be about 0.2 meters per second, and the median orbital period to be about 9.5 years. With this predicted distribution, we can determine how many of these planets an RV survey should detect by imposing detection limits on this joint distribution. The blue curve shows an example of an RV detection limit as a function of orbital period for a fixed signal-to-noise ratio and number of RV measurements spanning a given time baseline. Planets above this baseline with periods less than the duration of the RV survey are detectable, while those with longer periods might show up as long-term RV trends. To compare with the RV survey of HARPS, we use their actual published detection limits. We predict that the HARPS sample should harbor about one planet with a mass above one Jupiter mass and a period between roughly 3 and 30 years if the sample hosts an analogous population to that inferred from microlensing. The actual number of such planets found by the HARPS survey is indeed 1, in agreement with our prediction. We performed an identical comparison with the M-dwarf sample of the California Planet Survey, predicting the detection of about 4 or 5 giant planets. The actual detections reported by the CPS team are consistent with our predictions, both in number and properties, although the detection limits for the CPS sample are less well characterized than those of HARPS. So the fact that these numbers are consistent tells us that microlensing and RV surveys are largely disjoint, with only a small amount of overlap for orbital periods between roughly 100 and 1,000 days and planet masses above about a Jupiter mass. This limited overlap is such that, due to the steeply declining mass function, RV surveys infer a low giant planet frequency around M-dwarfs, detecting just the tip of the iceberg of the giant planet population inferred by microlensing. Knowing that these results are consistent, we can now combine the constraints from microlensing and radial velocities to derive planet frequencies across a very wide region of parameter space. This is a plot of the combined constraints on the giant planet occurrence rate around M-dwarfs as a function of log planet mass and log orbital period. If we add up the planet frequency in the area corresponding to giant planets, we find that 1 out of about every 6 or 7 M-dwarfs host a giant planet, with a period between 1 and 10 to the 4 days. This occurrence rate, derived from both microlensing and RV detection results, is much higher than the individual RV result of 1 giant planet for every 50 or so M-dwarfs. We can also compute the frequency of all planets with masses between 1 and 10 to the 4 Earth masses, and periods between 1 and 10 to the 4 days by integrating over the entire space, and in doing so, we find an answer of 2 planets for every M-dwarf. This is a very broad result, covering 4 orders of magnitude in planetary mass, and 4 orders of magnitude in orbital period. But perhaps more importantly, it demonstrates that it is possible to get a more complete picture of the demographics of exoplanets by including constraints from multiple discovery methods. In future work, we will build upon these results, comparing microlensing and direct imaging surveys to better constrain the population of long-period Jupiters and super-Jupiters, as well as the population of free-floating Jovian planets. If you are interested in reading more, we have presented these results in a pair of papers appearing on archive.org. The first paper mainly focuses on the methodology we developed, while the second paper details our comparison of the microlensing results with real RV surveys. Thank you for watching.